Each year, the Wonders of Physics has a theme, and this year, to show our sesquicentennial spirit, we chose physics of the late 1800s. To help us understand the state of science and technology at that time, we've asked Professor Dan Siegel of the History of Science Department here to give us some background. Professor Siegel?
We think of the 20th century as the century of progress. But if you had lived 150 years ago, in the middle of the 19th century, when the University of Wisconsin got its start, you would have been aware of progress too. It's just that things were not very far along back then. Our friend the horse was still the main means of transportation, whether on horseback or in a horse-drawn carriage or stagecoach. But progress was in the air. Steam trains had just started running from Chicago east to New York, and would soon push west to the Mississippi and then all the way to California. The main sources of lighting were still candles, oil lamps, and gas lights, but the promise of electric light was in the air. You could see spectacular demonstrations of electric lights in London and Paris, if you could get there. As far as the theory of electricity and magnetism was concerned, the basic laws had been discovered. But putting these together into a whole mathematical theory was still in the future, and modern communications like radio and TV could come only after this theoretical work in science had been done. In 1849, progress was a fact, and the future held promise, but horses for transportation and candles for light were still the rule, and the rest was still pie in the sky for your average Wisconsinite.
It's my pleasure to introduce the epitome of equestrian elegance, sesquicentennial splendor, riding Equus 99 V1.0.2, fully Y2K compliant, the nabob of natural philosophy, the 20th century's gift to the 19th, ladies and gentlemen, the man you've all been waiting for, the man who still makes you wonder about physics, Professor Clint Sprott.
Welcome to the Wonders of Physics. Mr. Lovell, would you put my horse in the stable, please? We are talking about physics of the middle of the 19th century today. You know, 150 years ago when the university was established, there was a lot of physics known, and we call it classical physics, and that's what we'll be talking to you about today. All of the areas of classical physics on the poster on the wall. And we're going to begin by talking about the physics of motion. Mr. Lovell, can you get that nag out of here?
Oh, now you've done it.
Oh,
You're
now
going to have to give him some of your traveling music.
Oh, all right. Well, I've always said Mr. Lovell is guilty of gilding the filly. But I would like to talk to you about the physics of motion. Now, motion goes back much earlier than 150 years. Some 300 years ago, the physics of motion was largely understood. And the first principle of motion requires a volunteer. Who will help? Okay. How about you? Come down here. Come over here and face the audience and tell us your name.
Diana.
Diana. Diana, have you ever gone bowling?
Yes.
Are you good at it?
Okay.
Okay, you're good at it. Well, that's good. But you know a bowling ball is quite heavy, right? Mm-hmm. Have you ever dropped one on your toe?
No.
Okay, well, we'll try not to do that. Diana, would you turn to your right, walk over to my assistant, Mr. Lovell. And we're going to take a bowling ball that weighs 16 pounds and suspend it from a wire from the ceiling and make what we call a pendulum. Now, what we'd like to do, Diana, one more. What we'd like you to do is to stand with your head against the wall.
If I can.
Stand up straight. Okay, now put that right at your chin and keep your head against the wall. Can you hold it?
A little.
And when I say I want you to let go, you ready?
Yeah.
Let go. Put your hands down by your side and don't move. Once more.
Help me.
Thank you, Diana. Now, this illustrates an important principle of physics that we call the conservation of energy. And this has been known about for many, many years. But we still use it today, and in many ways it's probably the most important of all the principles of physics. But it's used to explain the way things move as well as many other things. Now, that was an example of a pendulum, and there are many other kinds of pendulums that I could show you. Here's another pendulum that swings back and forth, but this one is on a spring. And so not only will it swing back and forth, but if I pull it down and release it, it goes up and down. And this is something called a Wilberforce pendulum, named after Lionel Wilberforce, who was a lecture demonstrator over in England around the turn of the century, who built these gadgets and used them to demonstrate principles of motion. Now, you notice a curious thing about it. For a little while, it goes up and down, but after a while, the up and down motion stops, and it's mainly twisting, as it is now. And then as you watch, the twisting is converted back into up and down motion. Now, I have a larger example of that over here. Here's a large Wilberforce pendulum, a mass on a spring, and when we pull this one down and release it, it will do the same thing. So if you watch that, the up and down motion will change into twisting motion, and the energy will go back and forth between those two kinds of motion. So watch that out of one eye while I call your attention over here to some other pendulums. Here I have two identical pendulums, this one and this one, but you notice they're connected up toward the top with a rubber band. And the reason is that the rubber band will couple the energy of one pendulum into the other. So suppose we start with one pendulum at rest, and we set the other one swinging like that. Now you notice as time goes on, the one on the left swings less and less, and the one on the right swings more and more. And that's because the rubber band is tugging on the one on the right, and it's tugging on it in just the right way to get it moving. And after a little while, the one on the right is swinging, but the one on the left is not swinging at all. And when that has happened, all of the energy is moved from one to the other. Now, as time goes on, the opposite will happen. The one on the right tugs on the one on the left and gets it swinging. And so, after a little while, the one on the right will stop and the one on the left will be swinging, and so forth. So this is an example of an important principle that we call resonance. This occurs so well because these two pendulums swing at exactly the same frequency. And as a result, one can transfer energy from one to the other very efficiently. Now, twice more before you leave the room today, I'm going to tell you about resonance. So I want you to remember that word, and when I ask you later on, maybe you can remind me what the word was. Here's another pendulum. It's a tennis ball, and it swings back and forth, much like the bowling ball. Not terribly remarkable, but there is something I can do to make this a little bit more interesting. If I stop this and push over underneath this pendulum some little blue objects and start it swinging again, at first it looks like it's doing pretty much the same thing. It swings back and forth, but as you watch it more carefully, you begin to notice a rather strange thing happening. The motion is somewhat more complicated. It's not simply swinging back and forth in a regular manner, but it's swinging back and forth in a much more complicated manner. Well, you may have guessed those blue things are in fact magnets. And two of them have their north poles pointing up, two have their north poles pointing down. And inside the tennis ball is another magnet that's attracted to two of those and repelled by the other two. And that makes a very much more complicated kind of motion. In fact, this motion is called chaotic motion. Now, people knew that there was complicated motion like this 150 years ago, but it's only been in the last couple of decades that chaotic motion has been understood in a detailed mathematical way. Here's another example of a chaotic pendulum. It's really a funny kind of a pendulum that swings back and forth, but you notice it has two arms on it, and one arm is rigidly attached, and the other arm is free to swing back and forth. So there are really two kinds of motion I can set this into. One kind of motion has this up and down, and this is doing all the moving, sort of like that. The other motion has this at rest and this swinging back and forth. But you see the two motions are coupled together in some way, and so if we start with it kind of up like this and let it go, you see a very complicated kind of motion ensues. And so this is another example of this chaotic motion that has now been understood in some detail, but there's still a lot of mysteries about this that people are studying. Now, the person who, in modern times at least, developed most of the theory, or a lot of the early theory about the way chaotic processes occurred, was a meteorologist at MIT named Edward Lorenz. And he pioneered the modern physics of chaos.
Oh, gracious sakes, I've got lost again. Where am I? Where's the horses? Where's the wagons? Have you seen the wagon train?
Well, yes, as a matter of fact, not 5 minutes ago, it went off to the east.
Off to the east. Let's see. Well, I've got a compass. Okay, I guess that's off this way.
Well, that's
they were
right.
going west.
Well, no, they went off to the east. But, you know, you brought in the compass, and we're going to be talking about compasses a little bit later in the day. But I noticed you brought some other things. What's in the bucket?
Well, I was out watering the horses, went down to the creek, and that's when I got lost.
Mr. Lovell, did we water our horse? We did. Well, you know, since we have a bucket of water, there is something we can do with it. Did you ever turn a bucket of water upside down over your head and not get wet? You've done that? Do you think we can do it right now? Okay, let's try it. That's not the way you do it, is it? How do you do it?
You have to swing it around.
You swing it around, don't you? Do I do it fast or slow?
Fast.
Really fast, right? Okay. And of course that's possible because of a law of motion that was developed over 300 years ago called the law of inertia. What else do you have in your bag there?
Well, I brought this can from the old country. I've been traveling with it a while, and it's the strangest thing. Whenever I push it away from me, it comes right back to me.
Well, that is strange. You know, I've seen a thing like that before. I'll bet I know how that works. And in fact, you could go home and make one of these if you want. I've seen these with like a rubber band inside and a weight, so that when the can turns, it winds up the rubber band, and that stores energy in the rubber band. And then when the rubber band unwinds, the energy is converted back into the energy of motion. So that's a good demonstration to illustrate the things that we've been talking about with motion and energy. What else do you have in there?
Got my kerchief in here that brought, and I use it to kind of wipe up the sweat and stuff from the trail.
Well, that thing's absolutely filthy. Let me see
Beg
that.
your pardon.
Well, do you mind if I wash this for you?
Well, do be careful.
I'm just going to put it in some of our special washing solution here. This will be quite harmless. You know, though, once we wash it, we're going to have to dry it. I wonder if you could light a candle there, and we'll use that to dry it once we have it good and clean. Now, this is very precious to you, you say?
Yes, it's my granddad's.
Yeah, well...
Be careful.
Oh, yes. Well, I wouldn't damage something that's so important to you. But it did get quite wet, didn't it? So let's see if we can dry it over the candle here. Well, it's not drying very well, is it? Oh, my goodness.
Uh-oh.
Oh, my goodness. Mr.
Oh,
Lovell,
my Lord.
Mr. Lovell, help me here.
Oh, gosh.
Help me here. Oh.
Oh, gosh.
Well, I guess it sort of survived, and it is pretty clean. But, you know, the reason we could do that is that the washing solution that I had over here is actually something you all have at home. It's rubbing alcohol. Or for you chemists, it's called isopropyl alcohol. Except it's not pure alcohol. It's a 50-50 mixture of alcohol and water. Now, you probably know that alcohol burns, but water doesn't burn. In fact, water puts out fires. And if you mix it in just the right way, half alcohol, half water, it burns, but it burns at such a low temperature that it doesn't set the cotton on fire. And so it's not very good at washing it, really. I just made a joke out of that. But it is a way to illustrate properties of certain kinds of liquids. What else do you have in there?
Well, I brought a little gift along with me. How about a can of nuts? You've been so kind to me.
Oh, I love nuts.
Where did that
Goodness,
come
you're
from?
playing a trick on me, I think. You know, I think you ought to have a seat and rest for a while, and maybe you can catch up with the wagon train a little later, and maybe you'll learn some physics while you're here.
Okay, I'd be glad to.
Well, thank you for your visit. Well, we are talking about the physics of heat and setting things on fire and things like that. You know, 150 years ago, people knew a lot about heat, but they didn't really know what it was at some deep level. But people knew that if you took a rod or a bar of something and put a flame on one end, of course, this end would heat up right away, but this end wouldn't heat up for a while. It would take a while for the heat to move from here down to here. And people thought, well, heat must be kind of a substance. They even gave it a name. They called it caloric. And they said, well, the caloric must be flowing from one end to the other like water flowing through a pipe. Well, these days we know that's not the right explanation. In fact, what heat is the random motion of the molecules that make up the object. It's a little like someone on the end row here got kind of fidgety, and then her neighbor suddenly got fidgety, and suddenly down the row, and after a little while, the one on this end is fidgeting. It's like you kind of respond to what your neighbors are doing. And that's what happens with heat. The molecules get fidgety in one end and make their neighbors fidgety. I actually have a demonstration of that here that involves a long rod, and right in the middle is a burner that will heat the rod. So I'm going to light the burner and begin heating it. Now, as you would suspect, this end is quite cold and this end is quite cold because the heat hasn't moved to the two ends yet. The middle, though, is getting hot. Now, you also notice that there are 4 marbles on either side, and those marbles are stuck to the rod with wax. Now, what will happen is eventually the rod will heat up and the wax will melt and the marbles will drop. Now, this turns out to be not one rod, but 2 rods that are connected at the middle, and the rod on this end is copper, and the rod on this end is steel. So one thing we'll be able to see is whether heat moves better in copper or in steel, because the one it moves better in, the wax will melt and those marbles will fall first. So this takes a little while, so I would just ask you to sort of watch that, and we'll try to pay attention whenever one of the marbles falls. But this is one way heat can move from one place to another, by heat conduction. Heat conduction occurs when something is in contact with something else. In fact, oh, very good. One of the marbles fell. Good. So when I touch these 2 tables, one is made of wood and one is made of marble. And if you've done this, you probably know the marble feels colder usually, doesn't it? And that's despite the fact that these are at the same temperature. Isn't that curious? And so when something feels cold, it doesn't necessarily mean the temperature is low. It could just mean that it's conducting heat more efficiently than something else. And a lot of what we sense as cold is really just heat being conducted away from our bodies, because our bodies are quite warm compared to most things. And so when heat is conducted away, we feel cold. Now, there's another way. So we've lost 2 of the marbles over here and none over there. Okay, another way heat can move from one place to another, besides conduction, is by convection. Convection is the process whereby heat moves because the medium, the fluid in which that is hot, moves from place to place. Now, a fluid can be either a liquid or a gas, and so the way you are being heated is because hot air is coming out the blowers there, and the hot air is moving from there over to you, and it is convecting the heat from where it's produced over to where you are, where it makes you warm. Now, I have a nice demonstration of heat convection here that uses another candle. There are many interesting things one can do with candles. In fact, there was a famous chemist. Oh my goodness, let's stop and talk about this. Have any of you been to Yellowstone Park? Yeah, Yellowstone Park was actually the first national park, and in 1872 it was established. And one of the reasons it was established was it had things called geysers. Have you seen those? Well, this is our artificial geyser. And it's produced by a source of heat down at the bottom, and there's some water in here. Do you know the temperature water boils at? Who knows? Who knows? Very good. 212 degrees Fahrenheit or 100 degrees Celsius. Very good. Except that's not quite right. Those are the right answers at sea level. If you go up on top of a mountain, or even in a city like Denver at 5,000 feet above sea level, water boils at a lower temperature. And the converse is also true. If you put water under pressure, it boils at a higher temperature. That's what happens in your pressure cooker at home. Well, that's what happens here. Here we have a column of water, and so way down at the bottom, the pressure is quite high. Like when you go down in a swimming pool, 6 feet down, you know there's a lot of pressure, right? And so as a consequence, the water doesn't boil when the temperature gets to 100 Celsius. It goes a few degrees higher. But eventually it does boil. When it boils, that relieves the pressure, and then it boils very vigorously. And when it boils, it sends the steam up into the air. The steam comes in contact with the cold air and condenses back into liquid water, and it rains. And the rain falls back into here, falls down here, and the heating begins again. Now, you know there's a famous geyser in Yellowstone Park. Do you know its name? Who knows? Yeah. Old Faithful. You ever wonder why they call it that? Not because it's old, but because it's faithful. It goes off about once an hour. And our geyser will also go off, not that seldom, it'll go off about once every 5 minutes until I turn it off after a little while. So you'll be able to see that go off a couple of more times. Look at here, we've lost all the marbles on this side, and we've only lost one marble on this side. So I think I'm going to turn this off before I lose all my marbles. So we have a candle going over here, and I want to show you something interesting that has to do with heat convection. Here I have a glass cylinder that's hollow on the two ends, and I want to lower that down over the candle and see what happens. Well, you see the candle flickers, and it quickly goes out. Now that's because the air that, for the candle to burn, it has to have a supply of air. In particular, it needs oxygen to burn, and the air comes in from below, and the candle heats the air above, and that air rises and goes away. So by putting this over the candle, it makes a tight enough fit at the base that no fresh air can get in. And so the candle is starved for oxygen, and it goes out. Now I'd like to repeat this again with one slight variation. This time, I would like to lower a small piece of metal down into the glass tube and lower it over the candle. And you notice this time the candle flickers, but it doesn't go out like it did before. And that's because we have now set up a convection current where the air is going down one side of the tube, fueling the candle, and then the hot air is going up the other side. And just to show you there are no tricks, I can take this out, and you see the candle quickly goes out. Now you may wonder why the air doesn't just go down and come up the tube now. And that's because when you have air, a stream of air moving this way and a stream of air moving that way, it has friction against itself. And so it doesn't like to do that very well. On the other hand, when we put a piece of metal there, the air can move by this nice smooth surface with relatively little friction. And so that's an interesting illustration of heat convection, which is the second way heat can move from place to place. There's actually a third way heat can move from one place to another. And the third way is very important because none of us would be here without it. And that's called heat radiation. And heat radiation is the mechanism whereby the sun heats the earth. You know, there's nearly a perfect vacuum in outer space, and so you may wonder how the heat of the sun gets all the way to the earth. And I want to show you how that happens using an apparatus here. Here I have a parabolic mirror, and in the focal point of this mirror is a match. Some of you can't see it, but most of you can see the match head. And over here we have another identical parabolic mirror, and in its focal point is a coil of wire through which we pass an electric current. And that makes it get quite hot. Now this takes a little while to heat up, but when it does so, the heat from that will be focused by that parabolic mirror, and it will go all the way across the room and be focused on the head of the match. So I want everyone to kind of watch the head of the match over there. And if you see anything happen, I want you to yell out so I can run over there and not miss it myself, because I want to be sure I see it as well. Now, while we're waiting for that to happen, I want to show you something else that involves gases. I have here some balloons. What do you think is in this balloon? Hydrogen, you say. Why do you think it's hydrogen? You don't know? Just a wild guess, huh? What do you think? Helium. Why do you think it's helium? Because it's lighter than air, right? It rises. And that's a good bet. But you know, hydrogen is another gas that's lighter, or as we prefer to say, it's less dense than air. And so it could be hydrogen. How would we tell the difference between hydrogen and helium? How do you think? Very good. Hydrogen burns. So one way we could test it is to try to set it on fire, right? And if it burned, we would say, well, maybe that's hydrogen. If it didn't burn, we would say, maybe it's helium. Well, that's not a proof, because there are many gases that don't burn that are less dense than air, and there are many gases that are less dense than air that do burn. But nevertheless, given that it was one of... Oh. So given that it's one of those two gases, we can test it by trying to ignite it. And I'm going to do that by putting a match on the end of a long stick, because I want to be able to reach up to it. And if it burns, I don't want it to be too close to it either. So we're going to let the match burn here for a moment, and then we're going to bring it up to the balloon and see if it sets the balloon on fire. Well, it popped the balloon, but you didn't see a flame or anything, did you? So indeed, that was a helium balloon. Would you like to see me do this again? I have another balloon. Okay, so we'll take another match and light it. Now, do you see Mr. Lovell with his fingers in his ears? If loud noises bother you, you may want to put your fingers in your ears. Is everyone ready? So indeed, as you might have guessed, that was a hydrogen balloon. And it went off quite explosively, didn't it? And you might have heard that there was a very large balloon called the Hindenburg many years ago that had hydrogen in it. And it exploded like that, and it killed a bunch of people. So people don't use hydrogen in balloons anymore, except for very special purposes, but certainly not where there's a danger that it will injure anyone. And this is the reason. People use helium or even hot air in balloons these days. Okay, well, while we're talking about various gases, I'd like to fill another balloon with this helium gas. Now, helium is interesting because it was discovered actually on the sun in 1868. And you may wonder how it was discovered there. It was discovered there by looking at the light that is emitted when it is heated to very high temperatures. So this is a balloon, and as you can see, this balloon is also less dense than air. It rises, and so you would suspect that this has helium in it, and indeed it does. Now, one of the interesting things we can do with helium is to actually breathe it. Now, I'd like to caution you. Most gases you breathe are harmful, so don't go home and breathe gases of various sorts. In fact, even the helium that you get at the zoo or the circus is not very safe because it's not sufficiently pure. And it often has contaminants in it that can be injurious to you. So I don't recommend that you try this, but we can do it here because we use special research-grade, high-purity helium. So let me breathe it and see what happens.
And as you see, it makes me talk a little bit like Donald Duck. Now, the reason is that sound travels about twice as fast in helium as it does in air. And as a result, it raises the natural frequencies of the cavities in my head, the resonant frequencies. And it makes me talk a little bit funny, right? Now, most people have seen that. How many have seen that? Pretty much everyone. But here's something you don't see so often. I have back here another gas. That's, in fact, very different from helium. In fact, in most ways, it's exactly the opposite of helium. Can you see what's different about it? It's a very heavy gas. If I tied it off, it would drop like a rock. This is a gas called sulfur hexafluoride. And I want to try to breathe this and see what it does to my voice. And again, this is another one of those gases that is safe to breathe only if it's extremely pure. So here we go.
And as you see, breathing the sulfur hexafluoride makes my voice sound very low. Now, the other interesting thing about sulfur hexafluoride is that because it's such a heavy gas, it stays down in my lungs for a long time. Not like the helium, which rises and goes out my nose right away. So as a result, I'll sound like this for the rest of the lecture, if you don't mind. But there actually are ways to get rid of the sulfur hexafluoride. We could have Mr. Lovell hang me by my feet and empty it out. Or no, let's not do that. Better yet, maybe I'll just bend over and exhale and see if I can get rid of some of it. Let's try that. And so I hope that makes me sound almost normal again. At least it always has. Well, we're talking about the physics of sound, and one instrument we often use to study sound is this gadget. Do you know what it's called? Who knows? What? That's right, it's called an oscilloscope. It's a little like your television set. There's a picture tube here,
and it makes wiggles, and you can see it's wiggling in response to my voice. And that's because this oscilloscope is connected to this microphone. So any sounds picked up by the microphone are converted into electrical signals. The electrical signals are displayed here. So you can see how very complicated the sound waves are that correspond to human speech. And that's as it must be, because in order to say anything interesting, the waveform has to be sort of complicated. Now, there are other waves that are not quite so complicated. Do you recognize this? What is it? Tuning fork, that's right. It's a U-shaped piece of metal. You strike it with a mallet, and it makes a sound. And I'm going to do that, but I want you to notice what it looks like on the oscilloscope. You can either watch here or on the television monitors. And so let's watch. You see what a very regular up and down kind of wave that is. That's called a sine wave. And a sine wave is the simplest kind of wave. It's a pure wave. It consists of a single frequency. Now, different musical instruments can play the same note, but yet somehow they sound different, don't they? And that's because musical instruments don't produce pure sine waves. I just brought one musical instrument down here, a recorder. Do some of you play this? A few people. I want to just play a few notes and let you see what they look like on the oscilloscope. So here we go. So you see it's quite a bit more complicated than the sine wave, but nevertheless the notes are identifiable. And so that's because it has additional sounds, additional frequencies that physicists call harmonics and musicians call overtones that contribute to the way a particular note sounds. Now I have here another identical tuning fork, and I could strike this tuning fork and you'll see it makes the same sound. But I want to do something kind of interesting. I want to put these two tuning forks nearby one another, and I'm going to strike this one and let it make a sound for a moment. And then I want to grab it and turn the sound off by touching it, and we'll see what happens. So you ready? Could you hear? This one was making a sound even though I hadn't struck it. Remember that word I mentioned early on? Resonance, that's right. These two tuning forks are in resonance because they are tuned to exactly the same frequency. And as a consequence, when this one makes a sound, this one picks up the sound very efficiently, and the energy from this one is transferred to that one because they're in resonance. Now, there's an interesting thing I can do. I've got a couple of weights on this tuning fork, and I can put them about halfway up here, and that makes the frequency of this a little bit lower. Let me strike it and see if you can hear the difference. Can you hear any difference? No. That's good, because the difference is very, very slight. You would have to have a very keen ear to hear the difference. But yet, let's repeat the experiment when I struck this one. Perfectly quiet. And so when they're out of resonance, the energy does not transfer nearly so efficiently. And this is what happens when you tune your radio receiver to the station of the transmitter. Then you pick it up. If you're tuned to some other station than what is being transmitted, you don't receive it so well. What do you think would happen if I'd strike them at the same time? Let's try that. Can you hear that funny sound? It goes woo, 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 doesn't it? Those are called beats. And whenever you have two sounds that are very close in frequency, but not quite the same, they will beat together like that. And in fact, musicians often tune their instruments by having one musician sound a note, the other musician sounds the same note, and then adjusts the guitar string or whatever until the beats go away. Because when they're exactly in tune, then you won't hear those beats. So this is another example of resonance, which we mentioned in the context of pendulums earlier. Well, I'd like to talk to you a little bit about electricity. Now, electricity was kind of in its heyday 150 years ago. Many things were known about electricity. People knew how to make electricity. They knew many of the properties of it. But a lot of the things we take for granted today, like electric lights and televisions and telephones, hadn't been invented yet, even though they were to come along later using the ideas of electricity. And one of the pieces of equipment that you often saw in lecture demonstrations and in laboratories in those days was a machine like this. This is a machine that makes static electricity. You've all walked across the carpet and touched the doorknob and had a spark, right? That's static electricity. And this is a machine that produces static electricity in a large-scale way. It was invented by two Germans named Tepler and Holtz. In 1878, they produced one of these, and it makes very large sparks.
by essentially static electricity. And this represents a voltage of maybe 30,000 volts or so. So it's a very large electrical voltage. Well, we don't use a lot of machines like this anymore, but it is a way that very large voltages were made in those days. Now, static electricity is still of considerable use in the laboratory, and people continued developing machines of that sort, making them bigger and bigger. And I have an example of something that dates to the 1960s. It's a static generator that is called a Pelletron. It was actually invented by a person right here at the University of Wisconsin named Ray Herb. And we'll turn it on. Makes a little bit of noise, but so whereas the Templer-Holtz generator produced maybe 30,000 volts, this produces several 100,000 volts. And in fact, machines of this sort have been made that produce tens of millions of electron volts. Now, I'd like to show you another demonstration of high voltage electricity. And this one requires a very brave volunteer. Who would help? Okay, come down here. Come right down here. Up. Okay, tell us your name. Angie?
Yep.
Okay, Angie, have you ever been out in a lightning storm where there's lightning and thunder and rain and all that?
I think so.
You've done that, huh? Does it scare you at all to be around lightning?
No.
It doesn't scare you at all. Well, you know, you should be careful because lightning can injure you. If it were to strike you, it would hurt you a lot. So, you know, when you see lightning, you shouldn't be outside. You should go indoors or something. Well, we're going to take you out where there's some lightning right now. You feel brave? You volunteered. We're not going to hurt you, Angie. Angie, would you turn to your right and walk right over to this cage and have a seat in what looks very much like an electric chair. Now, over to Angie's right is a 1,000,000-volt Tesla coil that produces bolts of lightning. And we're going to turn it on, and as long as you don't stick your fingers through the cage, you shouldn't feel a thing. Thank you, Angie. Now, the reason Angie could do that safely is because she was inside of something called a Faraday cage, named after Michael Faraday, a famous chemist and physicist who lived almost 200 years ago and actually gave lectures like this. And this is some of the apparatus that Michael Faraday used to demonstrate principles of electricity. And he had large cages of that sort that he put various electrical instruments inside of, as well as people. And so there is a moral here. If you're ever out in a lightning storm, a good, safe place to be is inside of a metal enclosure, surprisingly. In fact, your automobile is a pretty safe place to be, not because of the rubber tires, they don't do you any good, but because you are enclosed by metal. So even if lightning were to strike the car directly, the current from the lightning would go around the outside of you and not down through you. And so inside of a Faraday cage is a good, safe place to be. Now, we'd like to do another demonstration that involves this Tesla coil, but this is much too dangerous to ask for a volunteer. So instead, we're using one of our assistants, Mr. Paul Nahn, who for many years has helped us with this and other demonstrations. And you notice that Paul has a funny crown on his head, and the crown has little points on the top. And the reason for that is, in case any sparks were to come off of his body, we wouldn't want to catch his hair on fire or to burn his head. And so Paul has put that crown on. He's also putting some thimbles on his fingers for exactly the same reason. If any sparks were to come off the tips of his fingers, it could burn him severely. And so by having the thimbles on, the sparks, if they occur, will come off the thimbles and will not injure him. Now, you notice Paul has his shoes and socks off and a tray of water connected to the terminal of the 1,000,000-volt Tesla coil. Don't do this at home. You'll now see why we call Paul Nahn the human voltmeter. Now, Paul
was very brave to do that. But you notice he's taken the thimbles off his fingers. So to protect his hands, we're going to give him in one hand a discharge tube that's much like a fluorescent light with the coating removed. On the other hand is a 2,000-watt light bulb. Now you might also notice that over here in the audience, there's another fluorescent tube identical to the kind of fluorescent tubes that are in the light fixtures overhead. So once again, Paul Nahn, the human voltmeter. Okay, now this was possible because we use this Tesla coil, which is a very large transformer that uses a principle of magnetic induction that was developed by the same Michael Faraday that developed the Faraday cage and many of the other demonstrations that we're going to be talking about a little later in the day here. And Michael Faraday was a very important figure in science because... Well, who are you?
I'm Michael Faraday.
Oh my goodness, Michael Faraday in the flesh.
That's me.
Well, it's such an honor to have you here. We were just speaking of you.
Yeah. Oh, I see you have an audience. Are you giving a lecture?
Yes, we're giving a lecture on physics, and I understand you used to give such lectures.
Yes, I did. I always used to enjoy giving those lectures. Every Christmas, I would give a lecture to the general public. I really enjoyed lecturing to the children because they always have a bright idea of what physics is. So what types of things are you doing right now?
Well, we've talked about the Tesla coil, which was invented some 30 years after your death, but not to matter. It relies upon the principle of induction that you developed, and we have a very large cage here that is named in your honor, the Faraday cage.
I used to have one similar to this. I put equipment in it, and graduate students.
We still do that today.
I see things haven't changed that much.
No, not really all that much.
No.
That's true.
What other things do you have?
Well, we're going to be illustrating the electric generator and the motor a little
dynamo.
while. Yes, the dynamo, I think you called it.
And is this something similar to the apparatus Mr. Oersted had?
Oh, Mr. Oersted, indeed. We're going to be talking about him in a little while.
I see. Yes, I really never had a good handle on the mathematics of physics. I was a very good experimentalist, so I was able to do experiments and gather information from that. But I really am very bad at math.
Was that a handicap to you?
Very much so. It pays to know your math when you're doing your physics. I had to give my my notes and things to a Mr. Maxwell, who I guess came up with some very eloquent equations.
He did. I think shortly after your death, he came up with the basic equations that describe all of electromagnetism.
Well, that's very good. Very good.
Mr. Faraday, please report to your cage, please.
Will this do?
I'm sorry, I meant your carriage. It's parallel parked.
We had parking problems back then, too. Well, I bid you good day.
Well, it was such a treat. Thank you for your visit.
Thank you all.
Well, indeed, Michael Faraday died in 1867, but he did leave us an important legacy. He explained many of the things that involve how electric and magnetic phenomenon worked. And he mentioned a little demonstration over here that I want to show you. There was a time, around the time the University of Wisconsin was established, that people knew that there were electric phenomena and magnetic phenomena, but they weren't quite sure how they related to one another. And in fact, way back in around 1819, there was a Danish physicist named Hans Christian Ørsted who was giving a lecture very much like this. And he had been talking about magnets of various sorts, and he'd shown people the property of the compass. The compass, of course, has been known for thousands of years. Certain materials have the property that they orient themselves, if they're free to move around, so they point to the north, as this one does. But no one knew that this had anything to do with electricity, which had just been studied for a very brief time before that. But during the course of the lecture, Mr. Ørsted, after he had talked about magnetism, proceeded to talk about electric phenomena. And he had a wire, like we have here, and he connected it to a battery and caused an electric current to flow in it, much as I'm about to do here. And to his astonishment, the compass needle moved in response. And for the first time then, it became clear that electricity and magnetism were somehow related. And Mr. Oersted went back to his laboratory and he studied this further, and he came up with some basic laws that describe the relationship between magnetism and electricity. And I can illustrate that in another apparatus here. Here I have two loops of wire, single turn of wire, and I can make electric current go down one loop and up the other side, and then I can make a current in the loop that's nearby, and I can make the nearby current either go in the same direction in the two loops, or I can make them go in opposite directions. And when electric current passes through a loop like this, it makes a magnetic field. So one of these becomes like, they both become like magnets. And as you know, two north poles of a magnet repel one another, but a north and a south pole attract. So if I make the currents go in opposite directions, it turns out this is like two north poles of a magnet that repel one another. And you can see how they repel. On the other hand, if I make the currents go in the same direction, it's like having a north pole and a south pole toward one another, and they attract. Well, you may not have noticed this, even though you've dealt with electricity all your life. You've had many cords and things with electric currents in them, and you've never noticed them attract like that, probably. And one reason for that is that we have to use a fairly large electric current. There's about 40 amperes of current in these wires in order to make them do that. So it's a fairly small effect. But there is a way to make the effect much larger. And that is, instead of using a single loop of wire, you use a coil with many, many turns. And here we have an example of that. Here's a coil with several hundred turns of wire, and on the two ends here are magnets. And if I take this and rotate it in the magnet, look up on the television monitor, and you'll see a reading on the meter. And that means that we are inducing electric currents in this coil when it moves around in the magnetic field. And we can go the other way, and it moves the other direction. And this was the principle that was discovered by Michael Faraday, that in fact, if you move an electrical conductor in a magnetic field, a voltage is induced in it. And this is what eventually led to the production of electricity on a very large scale, because this is the electric generator, or dynamo, that powers all of our electricity today. All of the things that we have, that we take for granted, that use electricity, get their electricity from a dynamo that's turning like that, producing electricity by the Faraday effect. Well, a very interesting thing about this apparatus is that we can run it the other way. We can put a current in those coils, and if we do that by connecting it to essentially a battery back here, you see it goes around. And so the same apparatus can be used both as an electric generator and as an electric motor. In one case, we are putting energy of motion in and converting it into electrical energy. In the other case, we're putting electrical energy in and converting it into the energy of motion. And of course, electrical motors are also very important. Many things we take for granted these days, like electric elevators and washing machines and refrigerators and hair dryers and all sorts of things, have electric motors in them. And were it not for this principle of electricity, that electric and magnetic forces can act on one another, we would not have much of modern technology. So we can not only produce electricity, but we can convert it back into useful forms with things like electric motors. Now, another example of this, the fact that a magnet can exert a force on an electric current, uses this gadget right back here. This is another oscilloscope, very much like the oscilloscope there. It's a little bit bigger. And the way an oscilloscope works is back in the back, there is a gun that shoots electrons at very high speed toward the screen here. When those electrons strike the screen, it makes it glow. And the electrons, tiny particles that carry electric charge, carry with it an electric current, much like the electric current here. And one way we can illustrate this is to take a magnet, like a magnet here with a north pole and a south pole, and we can bring the magnet up near the electron beam, and we can make it move. And you see, it moves away from the magnet. And we can do the same thing with the other pole of the magnet and get a similar kind of effect. And so that's another illustration of the fact that magnets can exert forces on electric currents. So magnetism and electricity are two different things, but they are interconnected. They are related, and one can convert one to the other. Now, a very remarkable discovery was made in the late 1800s when people began to suspect that it might be possible to make waves of electricity and magnetism. Now, that's an interesting idea because you know about waves on water, you know about sound waves, but what does it mean to have a wave of electricity? Well, the discovery that indeed such things existed was made by a German named Heinrich Hertz, who around the latter part of the 19th century built an apparatus much like what we have here. Here we have two loops of wire. They're connected to some capacitors that were like the ones on the Templer-Holtz generator, and there's some balls here. And sparks will occur across right here, and that will generate electromagnetic waves. So this is like a transmitter. And our receiver is another identical apparatus over here that's not connected to anything. It's just sitting here on the table, free of everything. And so we're going to produce our electromagnetic waves over here, and we're going to try to receive them over here. And the receiver is not something you listen to with your ear, but there are a couple of little balls here that are going to have a voltage appear across them, and there should be a very dim spark that occurs there. And that's how Hertz was able to demonstrate electromagnetic waves. So let's try that. So do you see these sparks? Now, the remarkable thing here is that we can change the size of the receiving antenna by just moving this little rod down here. So we'll make it a little bit smaller. Now the electric currents in the receiver go around the small loop instead of the loop that was larger before. So if we try it now, you notice that there's no effect down here. And if we move it back to where it was, the effect comes back. And if we move it way down here, the effect goes away again. So this is an example of that word that I told you to remember. Do you remember what it was? Resonance, that's right. 3 examples of resonance you've seen today. The pendulums, the tuning fork, and now this apparatus. And this is very close to the kind of resonance that occurs when you tune your radio receiver to the station that's transmitting. And unless you're tuned to the exact resonant frequency, you get a very small signal. And so that's the way we can have all of these different stations broadcasting at once, and they don't interfere with each other because only the receiver that is tuned to the same resonant frequency as the transmitter picks up any significant energy. So the Hertz experiment demonstrated the existence of electromagnetic radiation. And the remarkable thing is that people measured the speed with which electromagnetic waves moved, and they discovered it was exactly the same as the speed that people knew light moved at. And this was very strong evidence that light is a form of electromagnetic radiation. And indeed it is, just at a different frequency. And so that's the last thing I want to talk about today is the physics of light. And I want to show you just 1 or 2 things. Around about 1855, there was a glass blower named Geissler who amused himself by taking glass tubes that were hollow and bending them into weird shapes and putting special gases in them and passing an electric current through them. And those became quite popular, and they were called Geissler tubes, and you could buy them, and they were kind of pretty. And I have some examples of these Geissler tubes right here. And I'm going to energize them using a small version of the Tesla coil that we had over there. It's a handheld Tesla coil, and when I turn it on and touch it to these things, I can make them glow. Now I'm going to turn off some of the lights. So those are Geissler tubes. And one remarkable thing about those tubes is that they make special colors. And depending on what gases you put in them, you get different colors out. Now, of course, not all light makes colors. A lot of light, like the light in this room, is white. And even 150 years ago, people knew that white light wasn't pure. It was made up of all of the different colors mixed together. And one way to demonstrate that is with a source of light here, a slide projector. They didn't have those way back then, but any source of white light will do this. And we pass it through a little triangular piece of glass here and display it on the screen up above. And we make a very pretty rainbow. And
in fact, it was Isaac Newton himself that first illustrated that light is made up of all of the colors of the rainbow. But you know, even 100 years ago, people knew that not all lights were like that. Some lights make only certain colors. And in fact, the light that comes out of a Geissler tube is an example of that. It's not white. It doesn't have all the colors. It has only certain colors. And we have an example of that I'm going to show you on the screen here. This is actually a mercury light that is producing only certain colors. You see a green color right here. Over here you can see a yellow. And way over here you can see a violet color. And this is the particular kind of light spectrum that comes out from when you pass an electric current through mercury vapor. And in fact, this was the way helium was first discovered. Helium, interestingly, was discovered on the sun before it was discovered on the Earth, and it was discovered because of the emission lines that it emitted. Obviously, we couldn't go there to see it directly, but by measuring the emission lines, one was able to deduce that that was helium. And in fact, the word helium comes from the Greek helios, which is the sun god. Okay, well, I would like to conclude with one last demonstration that, in fact, involves making for you a cloud. And in order to do this, we bring out some liquid nitrogen. Liquid nitrogen is a very cold liquid that's at a temperature of about 321 degrees below zero Fahrenheit, or 196 below zero Celsius. Or you could say it's a mere 77 degrees above the absolute coldest anything can be. And so it's very cold stuff, and it's a liquid, and what we do is pump gaseous nitrogen into this tank, and that forces the liquid, and also some of the gas, into this pipe on the top. Now, this pipe has several dozen small holes on the top, and the liquid and the gas come out those holes, and they cool the air above, because it's cold stuff, right? And when it cools the air, the water